Okay, so welcome to IIT Bombay Virtual Competitive Algebra Seminar. Today's speaker is Purna Bangere from University of Kansas. He will speak on Syzygies and Gonality. After the seminar is over, you can talk to him about various topics covered in his seminar. But during the seminar, we request you to type your questions in the chat box and we will relay them to Purna for his answers. So over to you, Purna.
Thank you very much, Jugal, for inviting me to this event, a competitive algebra seminar. And I always enjoy this and your enthusiasm, of course. And you have a, a small brigade of younger people who are so passionate about doing these things. Kriti Goyal has been so helpful. Thank you very much, Kriti. And can you hear me clearly? Yeah,
Yes, yes.
excellent. So my topic today is syzygies and gonality. This part, you can see my cursor here. Yes.
Yes, we can see the cursor.
Yeah. So syzygy is the algebra part, and gonality is the geometry part. So this is kind of a marriage of two themes from algebra and geometry. So let me start with the classical scenario, which dates back to last century. So let X be a smooth projective variety with a very ample line bundle L that gives an embedding of the variety inside projective space. So for those who are not familiar with this, it's a take a point of X and you have sections of L, that those are complex valued functions I work over C. So for each X, it goes to, it is a finite dimensional vector space, evaluate the basis, for example, one basis of this. At those points, you get R plus one uh, uh, tuple of complex numbers, and not all of them are zero because we are assuming it's very ample. So it defines a well-defined map morphism, and this morphism is actually an embedding because we are choosing it's very ample. So that's what our setup is. So once you have X inside PR, then you have the coordinate ring of X. So, and the question is that coordinate ring normal? So that coordinate ring will be, 1 minute. Oh, I'm trying to write a figure here. How do I write something here? Here. No, I can't write here, right? I thought I can write there. Okay. So
Yeah,
when
there is a pencil mark on the right. You can use mouse to write. Yeah.
I see.
On your right margin, there is a pencil mark.
This one? No.
Yeah. So with your mouse, you can underline something. Yeah.
Okay, does not matter. It's okay. In Zoom, I can actually write also. So when is the coordinate ring normal? So that means you have, even though X is smooth, the coordinate ring corresponds to the cone over that, and you have the vertex. Is the vertex is a singular point? Is that a normal singularity is the question. So when such a thing happens, we say L embeds X as a projectively normal variety. Is it, is the question. And is the ideal of this embedding generated by forms of degree 2. That's another point here. And the result, one of the first results is for projective curve, for a algebraic curve. So if we take a curve of genus G, then C is embedded as a projectively normal variety by L if the degree of L is sufficiently large, that is 2G plus 2. So this is Cashnova's theorem in last century, and the ideal is cut out by quadrics, also I showed. So this phenomenon of normality of the coordinate ring and the generation of ideal by forms of degree 2 can be viewed in a more general setting if you look at the syzygies of the ideal here. Syzygy. So Mark Green's work in 80s showed that these could be seen as special cases of a more general picture involving higher syzygies. So we will start with some definitions. So you take the setup as I mentioned before, and let S be the homogeneous coordinate ring of X in PR, and look at this ring here, direct sum of H naught of B plus ML. Then R is a finally generated S module, and you have Koszul complex. Yeah, where RQ is the rth graded piece of this graded ring. And then you have Koszul cohomology. So take at the right stage the kernel divided by the image. So that is the Koszul cohomology group corresponding to this embedding and the resolution of S. So this is what we will be interested in, these Koszul cohomology groups, the computation of which is our main concern in problems such as this. R also admits a minimal graded free resolution. So let's write R is S mod I. S is the coordinate ring of X in PR. So you have a finite minimal graded free resolution, and it has this twist. So Green, what he calls as a Syzygy theorem, it's not Hilbert's Syzygy theorem, it's a Syzygy theorem. He says that this Koszul cohomology groups are finite dimensional vector spaces, and how many twists are there here? That is this direct sum. How much in this direct sum is measured by these Koszul cohomology groups? Yeah. So when you say that a Koszul cohomology group is 0, that means there is no such twist. This P minus Q. If this is 0, this Koszul cohomology is 0, that means there is no such twist. So these numbers are called graded Betti numbers. And there's a compact way to express them using a table called the Betti diagram, whose pth column and qth row contains the entry BPQ, that is dimension of this. So let's look at this. So it looks like this. So yeah, so we'll take some examples and it becomes clear. So let's first see some result of Green, which helps us in reducing the dimension of the variety and go to ultimately to perhaps curves. So assume L is ample, globally generated, and arithmetically Cohen-Macaulay. That means that the coordinate ring is having all these properties. And you take a smooth member in this linear system of L, which exists by Bertini's theorem. Then the Koszul cohomology of L can be reduced completely to the hyperplane section. That's what it says here. And there is a thing called Koszul duality. So it's kind of in the Betti diagram, you can reflect things from far right to far left. So that is given by this. This is a technical result which we will not bother ourselves with too much. It's going to be used, is what I wanted to say. So let us look at this in terms of resolution. So remember, there was when I went here, I took this, when I took the graded ring, I had this B here. For our purposes in this talk, B will be, it's a line bundle, any line bundle. B will be, it's called a scaling factor. For us, B will be either a trivial bundle or its canonical bundle of the variety. Okay, so set B equal to OX. We define the following terms. L is projectively normal if in the free resolution E0 term was S. And L is normally presented if the ideal I is generated by quadrics. And L satisfies property NP, as Green introduces that notation. NP if in addition to satisfying property N1, the resolution is linear till the peak stage. So NP property generalizes these two notions about projective normality and generation of quadrics. And the reason we geometers are interested in is the property NP many times conjecturally, and some of the times what by the results that have been proved since 1980s, the failure of property NP captures a certain geometric property, and that's why we are interested in this in whether a embedding satisfies property NP. We'll come to that soon. Well, at the later part of this talk, after I set up everything. It is customary to denote KPQXL, that's the Koszul cohomology group, by when you take the scaling factor to be OX, we just write this. So this is a theorem due to Green. If L satisfies NP for P bigger than or equal to 1, L satisfies property NP if and only if L satisfies N naught and all these Koszul cohomology groups are 0. This is a theorem, it requires proof. I'm not going to give that, I will just state it. So the vanishing of the Koszul cohomology group is equivalent to L satisfying property NP. That is the resolution of the minimal the graded free resolution of the coordinate ring is linear till the peak stage. So L satisfies property NP. How does the Betti diagram look? So Betti diagram looks like this. So you have so many quadrics, so many cubics. Until peak stage, you have all these cubics, and then relations among cubics is linear, and it's linear till the peak stage. That's why you have all this 0 here. There are no other twists to the in the free resolution. This is it looks like direct sums of S minus 2, direct sums of S minus 3, and direct sums of S minus P minus 1. Till the peak stage, that means these are all the other twists are 0 here, and then something else might happen after the peak stage. So a Betti diagram of a embedding which satisfies property NP looks like this. This means this dashes means zeros. These are all zeros. The star means it can be anything. Yeah. Let's take some examples. Take a rational normal curve. So take P1 inside a projective space PD embedded by, say, complete linear series of degree D line bundle on P1. So how does its resolution looks like? So if you take, for example, in P3, resolution of the coordinate ring of P1 inside P3, twisted cubic looks like this. So you have this projectively normal, and it is generated by quadrics, 3 of them. So that's why you have the Betti diagram here, 1 plus 1, that is 2, that's the twist here, and 3 such twists here. Is direct sum of S minus 2s. And what about the relations among these quadrics? That is linear. So it is S minus 3. 1 plus 2 is 3 minus 3, and there are 2 such copies of it. So this, as you can see, satisfies infinity in some sense. It satisfies property N1 and N2. It's completely linear. This is because of a more general phenomenon because the P1 inside PD is here, this embedding is a variety of minimal degree. So when you have a variety of minimal degree, the resolution is always linear until the last stage. In fact, I remember this when I was a graduate student, Jugul telling me this fact about minimal degree. This was 30 years ago. Yeah, in Italy. Trieste. I remember this. Okay. So, in fact, it's if and only if, I think, as because of if it's a variety of minimal degree, then you have n infinity, namely the Syzygies is linear and throughout. Generalizing the above, one obtains the Betti diagram for a rational normal curve. So it's completely linear, as you see. There's nothing in between, nothing below this. So and it is if you take R here, D equal to R, you have linear till the R stage. That means that means you have quadrics, and relations among quadrics is linear. You have cubics, and relations among cubics is linear. You have quartics, and so on. But unfortunately, this is no longer true if you take even genus 1 curve. So let us look at elliptic curve here. So you take an elliptic quartic curve, degree 4 line bundle on an elliptic curve, embed it inside P3. You can show that it actually embeds inside P3. It's very ample, and it's the ideal is actually cut out by quadrics. It's actually exercised in Hartshorne, and the relations among quadrics is it's not linear. In fact, there's a complete intersection of two quadrics. So this is a Koszul resolution here. And the relations among quadrics is not linear. So we have a jump here in the twists. And why that jump? There is a geometric reason for that. Is the idea here. So the Betti diagram looks like, so at this stage, it's 1 plus 1, that is 2. Yeah. But then you see the relation jumps there. If it were n 2, there would not be here, and there would be something here. 1 plus 2 is 3, but there's no 3 term. That's why there's a 0 here. So 2 plus 2 is 4, and there's a twist of minus 4, and there's one copy of that. Any questions? I don't see a question. So let me move on. So this satisfies, so a quartic curve has property n1 but not n2. So a line bundle of degree 4 on an elliptic curve satisfies n1 but not n2. So let us look at a case of, so we talked about P1, right? P1, that's the rational variety of dimension 1. What about rational? Let's go to surfaces and see what happens for rational surfaces. Things get extremely complicated already. So let us take a rational surface such that minus k is effective. These are called anti-canonical rational surfaces. For example, P2 is, you blow up a P2 in 9 general points, it still be anti-canonical. In fact, it will be Fano for till 8, blow up of 8 points. And then if you keep on blowing along the cubic in P2, you will still have as many points as you want. You still have the anti-canonical property. That means minus k will be effective. So if you take such a rational surface, whose presence is also ubiquitous among in the geometry of algebraic surfaces, so yes, let us be a rational surface, anti-canonical rational surface, and let L be an ample and base point free line bundle. This is a old result of mine. I'm just recollecting some of this to give a context for the results that's going to appear. So L satisfies NP. That means you embed L in, you embed X, the surface, embed the surface S inside projective space using the very ample line bundle L. Then this is G is linear till the P stage if and only if actually. Oh, sorry, this, excuse me, sorry. So this is for any rational surface. Yeah. So for any rational surface, if minus k dot L is bigger than or equal to P plus 3, it satisfies NP. If S happens to be in addition anti-canonical, then it's if and only if. Yeah, that's the point. So this is a sufficient condition for a line bundle on a rational surface to satisfy property NP. And it is a complete characterization if it is anti-canonical. Yeah, this is in Crowley Journal in 2001. This paper is dedicated to Mohan Kumar, I think. So yeah, this is minus k dot L bigger than or equal to P plus 3. So it's here, it's a very interesting point here. This opens up various things. Let me explain where the geometry comes in. On the left-hand side, you have a algebraic property. On the right-hand side is purely intersection numbers on surfaces, which is geometry. So that means a something that is very extrinsic. NP property is extrinsic. It depends on the embedding. And this is an intrinsic property because it It's about the intersection numbers of curves on a rational surface. So that's the intrinsic property of the surface. So this extrinsic property is very intimately related, if and only if actually something happens at the level of intersection of curves on an algebraic surface. Now this result has numerous corollaries. One of the interesting corollaries, which I'm not going to state, but state it in written form here, but I'm going to explain in speech. So I hope I speak slowly so that you follow. In the classification of algebraic surfaces, one of the most important things is what is called as termination of adjunction. So if you take a Kodaira dimension negative infinity surface, if you keep on adding, take a line bundle L and you keep on adding k to that, ultimately H naught, there it has no sections. H naught of mk plus L, it has no sections after m large. Okay, so given a line bundle L, there is an m, so that if I keep on adding k at m times, then it loses all its sections, however positive L may be. This is a very important part of classification of algebraic surfaces, termination of adjunction, it says. And for rational surfaces, it's also true. If you have an ample line bundle L, if I keep on adding m times, if I keep on adding k, copies of k, so L, I have L plus k, L plus 2k, L plus 3k, so on. So finally what happens is L loses its ampleness. So it's called termination of ampleness and termination of adjunction. Given a line bundle L, can you tell what m what m I should add? What multiple of k that I should add to L so that it loses its adjunction? I mean, where there is a termination of adjunction. That was done by Siliberto a long time ago. Using this, we can express this completely in terms of extrinsic property NP. So what I'm saying is, if you have a line bundle, very ample line bundle L, and you embed it inside projective space, it loses its. There's a termination of adjunction for L with the effective termination of adjunction depending on what NP property it satisfies. That's what one of the corollaries of this is. So there's a geometry involved. That's a termination of adjunction is a very geometric property, and ampleness as well. And that is a very intrinsic property, and that is related to NP property. So that's one of the places where geometry appears. So of course, this result recovers some of the results of Artovian inequality. This result is for any Pn, but for P2, it recovers and sharpens, I think. So now let us look at so rational surfaces form a very small part in the geography of algebraic surfaces, and most of the surfaces that we come across are what are called as general type. That means the Kodaira dimension is 2. So these correspond to genus 2, bigger than or equal to genus 2 curves. So almost all curves have genus G bigger than or equal to 2, unless of course you take an elliptic curve, but you can G equal to 0 is rational, G equal to 1 has Kodaira dimension 0 for curves. So most of the curves are general type. So similarly for surfaces, most of the surfaces are general type, which are Kodaira dimension 2. So what are the NP results for such surfaces? So a surface of general type, it has maximum Kodaira dimension. That means it's for a surface that has canonical big. It means if you take a large multiple of canonical, the image is again dimension 2. If you take a minimal model, you have NEF as well. So this determines the Kodaira dimension actually. So if you, for example, just to look at the density of these surfaces, if you take P3, any hypersurface of degree bigger than or equal to 5 is general type. So as any genus G bigger than or equal to 2 is general type for curves. For example, any surface in P3 whose degree is bigger than or equal to 5 is actually general type. Now we state two theorems on higher syzygies of adjoint linear series. So when you look at Castelnuov's theorem, what did it say? Castelnuov's theorem said if you take a line bundle of degree bigger than or equal to 2g plus 2, then the ideal is generated by quadrics. 2g plus 2 can be written as 2g minus 2 plus 4. Right? 2g minus 2 plus 4. What is 2g minus 2? That is degree of the canonical. So if you have a line bundle on a curve whose degree is at least canonical plus 4 points, or a line bundle of degree 4, if at least canonical plus 4 points, then it satisfies n1. So that gives a motivation for conjectures on surfaces. So for example, Mark Green, I don't know why I can't write here. See, it says something here. I don't know, it says type. I wonder how I write here. And on Zoom I can write. I thought I would be able to write here. I can't for some reason.
Yeah, with this icon you will be able to type, not yeah, I am familiar with this. Okay. But anyway.
Fine. So I can't type. So the Castelnuov's result on curves was generalized by Mark Green. He said that if you take a line bundle L on a curve of degree at least 2g plus 1 plus p, then it satisfies NP. 2g plus 1 plus p. So 2g plus 1 plus p can be written as 2g minus 2 plus p plus 3. Right? 2g minus 2 plus p plus 3. So if you take a line bundle L, which is at least as positive as canonical plus p plus 3 points, then such a line bundle satisfies property NP. That's a result of Green on curves. So canonical plus p plus 3 points. So a point on a algebraic curve is, for example, a point is ample. So if you take any line bundle on a curve, which is at least as positive as canonical plus p plus 3 times ample line bundle, satisfies NP. So this led Mukai, Mukai's conjecture, Mukai, Mukai, to conjecture that if you take an algebraic surface, if you take any line bundle which is as positive as kx plus p plus 4 ample line bundles, that should satisfy property NP. So it's called Mukai's conjecture. It's completely unknown as in its full generality. This is one of those first shots at this theorem that you're going to see. So this gives a Mukai's theorem for it's kind of open set in the PIC. If in addition you assume in addition to ample, you have to assume base point free, then and b minus k is nef, then you say that Mukai's conjecture is true. Well, slightly better bounds, but a stronger hypothesis. If you take very ample line bundle, instead of base point free and ample, Ein and Lazarsfeld have a general result for any variety about NP property of the adjunction line bundles. But if you even relax a very ampleness to base point free and ample, the situation becomes extremely difficult because you don't have projection techniques that we have for very ample line bundles. So this, for an open set in the PIC, you can say that roughly that such a bound can exist. So if you take a line bundle L on it's for regular surface we have stated, but it is true for irregular as well. But there are little more different assumptions, so I didn't want to clog the talk with technical things. So this is a clean result. So I just wanted to state for regular surface. So K plus B tensor N satisfies NP. So this recovers a lot of results. For example, if you take this B to be 2 times K, for example, multiple of canonical, then it recovers results of Kodaira and Bangere and improves their results on projective normality of pluricanonical line bundles. It gives a much better bound than the results. For example, 5K is very ample for a surface of general type. If you assume this is missing some assumptions, you can assume that this general type need not be smooth, can have at most cannot have at worst canonical singularities. So I can assume canonical is ample by going to the canonical model. So then we can say that 5 times k is very ample, that is well known. That's a result due to Bangere, and he had shown that 6k is projectively normal. Earlier, Kodaira had proved for 8k, and it was improved to 5k by Chiliberto, and it recovers those results and shows higher syzygies for pluricanonical, which are optimal. But this is a much more general result for any adjunction line bundle. This is in Canadian Journal. This paper, I think, is dedicated to Bauman Murthy, if I remember right. So, and also, what about if I replace B by ample? So there is something called effective Matsusaka result. So it's very Japanese people, it's a lot of Japanese names are involved in this. Matsusaka was in Brandeis when I was there. I used to talk to him. It was a pleasure talking to him. So he actually pointed out once to me his effective result. So this is effective Matsusaka result, it's called. So we use that to show NP property, because we can show there are effective Matsusaka says that if you take a large multiple of M, it becomes base point free, large multiple of an ample bundle. What multiple it is given by this bound here. This result is due to Fernando Dulbesto, effective Matsusaka for surfaces, and we use that to give for an ample bundle instead of base point free and ample. This result is much weaker than this result because this is a uniform bound. Here, you depending on the A. This is true for any base point free and ample satisfying these two conditions, which is open condition in the PIC. But this is not the case here. Now, we were talking about NP property. Now we go talk about MP property. This is it's kind of a other side of the Betty diagram. So let's look at this definition. Let X be a smooth projective variety with a very ample line bundle L. We say that L satisfies property MP if this Koszul cohomology group vanishes for all k bigger than or equal to this. It seems technical, but it's kind of nice actually. So MP property means, so NP property said something about zeros here. MP property says something about zeros here. If you take curves, then it's because it's a 3 regular line bundles are ruled surfaces, there'll be only 2 rows. So then then all of this below will be 0. So take curves, so it will be just, it's kind of a reflective property, MP. So if you have Gorenstein, embedding is Gorenstein, then you can reflect it, this Betty diagram along the middle. So MP property is about zeros from the right hand side of this. It's kind of a anti-symmetric to NP, and it has its own geometry. So that is what we are going to be talking about in this talk. I just wanted to say here, as B minus K NF, there are generalizations of this result with Krishna, who is here in the audience, which we will not go into. So there is a stronger version of these results in some sense. So MP, so we are going to be talking about MP property, which reflects something about what is called as gonality of a curve and higher dimensional varieties. So we are going to be talking about that. So it will get a little technical, and unfortunately, I thought I could be able to write, and I can't, and it is a it takes away some of the juice of my talk because I wanted to say some things using my pen and I can't. So it's okay. Should have prepared properly. So MP property, there's a criterion by Aprodu and Lombardi, and we will be talking about that for the next few minutes. So it seems a technical result, which it is. So you want to show some Koszul cohomology group to be 0. And then you have some zeros on the second row of the Betti table. Yeah. So it says something about the free resolution. What are it gives what is the geography of the free resolution from the right side. So if you have something which satisfies MP and MP, you have a more complete picture of the free resolution. That's one of the things that you're talking about. Okay, here. Let X be a smooth projective variety of dimension n bigger than or equal to 2, and let L be an ample and globally generated line bundle. Set R equal to this dimension of this vector space. Let Kx be the canonical bundle of X. If these multiplication maps are surjective, then this Koszul cohomology group vanishes. In particular, we have certain M P property. It's not MP, it is M some R. So for example, so we want to say it in terms of P here. In the situation of the lemma above, this Kp1 is 0 if for P bigger than or equal to R minus N by Green's theorem. There's a theorem of Green which states that this is 0 for P bigger than R minus N. The surjectivity of the above map for all P less than or equal to P in this range 0 to K implies that L satisfies property Mk plus N. So that means the second row. So let me, Mk plus N is this, so many zeros you will have coming from the right. So this, we need the subjectivity of these multiplication maps, which will imply certain Koszul cohomology groups to be 0. Okay. Recall that G1D is by definition a pencil of degree D, and the gonality of a curve C is given by this. In some sense, take for example hyperelliptic curve. Hyperelliptic curve after P1, the next one in line is, and of course you have genus is G equal to 0, that is P1, genus G equal to 1, that's elliptic curve, and then general type curves, genus G bigger than or equal to 2. There are other measures of how close something is to P1. So take hyperelliptic curve. For example, genus 2 curve. Genus 2 curves always admits a 2-to-1 map to P1. So its gonality we say is 2. So it has, so if you given a curve C, you can have various degree maps to P1, rational map to P1. It may not be morphism, C to P1. Look at the lowest degree that is allowed. That will be the gonality of the curve C. So it's like that much closer to P1 in a certain sense. So that's called a gonality. It's very geometrically relevant, important. For example, hyperellipticity of a curve is an important geometric property. So this has been generalized to higher dimensions, the notion of hyperellipticity by Fujita, and more recently it has been carried further, results of Horikawa, to higher dimensions by Me, Chen, and Gallego. So the MP property is closely related to this geometric property. This geometric property is closely related to MP property. So something is intrinsic, and that's kind of coming from an extrinsic entity, like a free resolution. So if you take a failure of MP, if you take a degree is bigger than or equal to 2G plus 1, for example, M1 fails if and only if X is P1. So if we take 2g plus 2, then m2 fails if and only if x carries a g12. See, you see, it's see how it is. If you take a line bundle of degree 2g plus 2, it always satisfies n1, but it doesn't satisfy m2 is what it's saying. If and only if it carries g12, that means it's hyperelliptic. So this m2 fails for a line bundle of degree, say 2g plus 2, if and only if the curve is hyperelliptic. So this m2 is capturing the hyperellipticity of the curve. So it is gonality. So that's a very geometric thing, and this is a very algebraic thing, and they're married here. That's the beauty of this conjectures and results. So gonality conjecture of Green and Lazarsfeld says that MP, if you take a line bundle which is sufficiently large, degree on a curve, then MP property satisfies, it's an MP fails if and only if P is bigger than or equal to gonality of C. This is not proved yet. There are effective bounds on this. So as you can see, a purely algebraic property on the left, and this is a geometric property, and they are married by this conjecture. And this is a result above here. It is not so hard to prove that if x carries g1p, then no line bundle of degree 2g plus p can satisfy MP. Okay. So Hein and Lazarsfeld show, so this was supposed to be 2g here. If you take a large degree line bundle, then this Koszul cohomology group satisfies if and only if B is P very ample. So this is something about gonality here. I mean, sorry, this is something about kind of gonality, and here it is a purely Koszul cohomology. So P very ample is a geometric property, and that is coming from a certain emptiness of a line bundle. So what is a P very ample means? So P very ample means if you take a scheme of length P plus 1, this map surgeons. So very ample is a particular property of this. If you take 2 points here, if you can separate 2 points and tangent vectors, you have very ampleness. So here you want to surjection for any P plus 1 length scheme. Then we call it a P very ample. It's a generalization of very ampleness. And that is reflected in certain Koszul cohomology group vanishing, which in turn implies something about the free resolution. Yeah. So gonality conjecture follows if you take P B equal to Kc. So this theorem of Lazarsfeld and Hein is not an effective bound, but for a very large. So it is if you take B equal to Kc, it recovers the non-effective version of the gonality conjecture, and that bound Lazarsfeld and Hein had proved for large degree line bundle without giving effective bound, and Rathmann has proved 4g minus 3. The original conjecture is 2g, but this is a nice result. Of course, the effective gonality conjecture improved versions is still open. So we are going to now talk about MP property for general type. So to take a smooth and regular projective surface and let B be an ample and globally generated line bundle on X, then RB satisfies property MP plus 2 for all R bigger than or equal to RP plus 3. And this result is optimal. So in particular, if you take a smooth regular projective surface and B is an ample and globally generated, you can improve this bound is what we are saying. So if you take R is bigger than or equal to P plus 2 instead of P plus 3, this result above comes from considerations of Castelnuovo-Mumford considerations and Castelnuovo-Mumford bounds regularity, Castelnuovo-Mumford regularity of line bundles from Mumford's theorem. This follows. But if you want finer results, you have to have these kind of conditions. This is kind of optimal, but it's not clear whether in what generality these MP properties are true. There are no conjectures for that. So here is the first result. We say, in some sense, B minus K Nef, for a, what I'm saying is, if you take a general member in the PIC, then this is all satisfied. And you have this MP plus 2 property. But people are interested in for adjunction line bundles, K plus. So we have here, this is true for any surface of general type, but I'm taking regular so that I have a clean statements. So if you have let X be a regular, this is a joint result with my two students, Devaditya and Jayan. It says that if you take a regular projective surface of general type with at worst canonical singularities, and B be an ample and globally generated line bundle, assume the non-specialness of this line bundle, and you have this inequality, then K plus RB satisfies property MP plus 2 if R bigger than or equal to P plus 1. There are various other generalizations we have of this result for higher dimensions. I'm not going to state, just I will leave this with this clean statement here. So in some sense, if you take 3B minus K is Nef, this is satisfied, for example. This result is optimal. If you relax this condition, then this fails. But by no means I'm saying that this is the ultimate result. No, it is one of the first results in this field, which is satisfying property, which is concerning property MP as opposed to NP. So we are saying about the right side of the resolution. My results with Krishna shows that there is a NP property associated under this hypothesis. So together with that and this result, you can say how the resolution looks like of the second row, for example. A more complete picture of the resolution emerges. Okay. What is going on? Basic sketch of the proof. I'm not so sanguine about giving a proof. I want to say some other result here. So let X be a smooth projective variety. L is a globally generated line bundle. Then you have the Syzygies bundle ML. So everything is dictated by the Syzygies bundle, the Koszul cohomology vanishing associated to Syzygies bundle. That is what it's saying. So but that is Aprodu and Aprodu's theorem and Lombardi's theorem reduces that to some surjectivity of some multiplication maps, which in turn shows a vanishing of certain Koszul cohomology groups involving ML. So what we show is it essentially vector bundle techniques. We have to prove some surjectivity of some maps, and we show that. And we show that by going to curves in a way which is sometimes not canonical approach, and there is no such canonical approach because these varieties are not arithmetically cohomology embedded by K. If you take these adjunction bundles and embed the surface of general type, those in general are not arithmetically cohomology, so you cannot just go to curves as you want, taking the hyperplane section. You have to go much more cleverly using various homological techniques. And then once you go to curves, then you have that ML, Syzygies bundle, ML restricted to some curve you are chosen, and it's a particular curve, and that is no longer going to be stable bundle. Mehta-Ramanathan theorem shows that if you take a ML and restrict it to a curve, it will not, their stability is not preserved, and that is preserved for only very large degree, subvarieties. But here these are very small degree subvarieties, and it will not be stable. So what we have to do is when we restrict those surjectivity maps to curves, this bundle, the ML becomes, say, unstable. So this technique here we take a Harder-Nurseman filtration kind of a object, not exactly that, and then we reduce everything to curves by a series of homological techniques. So that is what this lemma is about. Once we do that, then we have this is reduced to multiplication map of vector bundles on curves, and then there are results about surjectivity of multiplication map of vector bundles on curves, and then we use those results, invoke these results. It's a complex induction, but I just gave a sample of that. And the results are kind of optimal. Like a Hirscher-Brook surface, for example, that is a rational surface fibered by P1 over P1. This is Fe. It's a Hirscher-Brook surface. So those give a optimality, those surfaces and line bundles on it. So you take a line bundle LAB, that is AC naught plus BF. You remember it is actually fibered by P1 over base curve P1. So you have a horizontal component and a vertical component. Horizontal section, we call it as C naught, and vertical fibers are called F. So you take AC naught plus BF, that is the line bundle L. Take a smooth curve in that line bundle, which will be very ample for our purpose. Take a smooth curve. That, by uproduced result, we know is agonal. And what we show is that Fe is a regular surface. That is, its H1 of OFE, H1 of its structure shift is 0. And using Lefschetz theorem of Green, Lefschetz theorem has been proved by many other people. That principle is known by Lefschetz theorem going to hyperplane. So using Lefschetz theorem of Green, we can show that L satisfies MP if and only if this satisfies property MP plus 1. So by uprodu, this is C is agonal. If you take a line bundle L, that curve is agonal. So this is saying if and only if it satisfies MP. So that is saying something about gonality of those curves together with uproduced results. So there's a purely algebraic side here of the resolution of the minimal free resolution where the zeros are from the right end of the Betti diagram, and here is a purely geometric entity about gonality of the curves in the linear system. We are saying that gonality is dictated by this here. So putting these two, it's an optimality result. So what we have shown that about that regular surfaces, we've proved the results here is optimal, is what we are seeing. This result. This result is optimal, is what it's saying. Let us. I want to make a brief statement about some interesting varieties here. So these are all smooth varieties we are talking about, but we want to deal with the much greater generality. We take any scheme, and schemes are perfectly fine objects, and especially schemes coming from vector bundles. So take a reduced structure, reduced connected scheme, and assume you have a line bundle or a vector bundle on Y. A ribbon on Y with conormal bundle E is a scheme structure. It's like a doubling such that I square is 0. So Iy is the ideal of Y inside this scheme here, Y tilde. So Y tilde is the ideal of Y inside the reduced part inside the non-reduced part. So if that is a line bundle and its square is 0, then we have a double structure. It's called a ribbon, and they have a ubiquitous presence as well in the geometry of algebraic surfaces, curves and algebraic surfaces on higher dimensional varieties. And so they come naturally. What about them? Can you say something about gonality and Syzygies property for those? So what we show here is one particular interesting such ribbons we deal with here. let Y be a smooth projective surface, and you take a non-reduced structure on that, assuming certain cohomology vanishings, we have this kind of a diagram. So we can show that there is a thing called MP property we defined for smooth. We can also do it for non-reduced structures. So what we are saying here is, if there's an interesting point here, if you take a non-reduced schemes coming from vector bundles on smooth schemes, and then you take a line bundle on that non-reduced part, what about that MP property of that? Because which is related to gonality. We say from this that if you have NP property in the reduced part and the MP plus 2 property of the reduced part, then we have NP property of the non-reduced part. So that is what all this is saying. So in particular, there are something called K3 carpets. These are very important for reasons which will become soon clear. These are like fake K3 surfaces. K3 surfaces are interesting. They've been studied in great detail, and it seems to generate a lot of interest. So these are K3 carpets are in the boundary of the moduli, at least of the Hilbert scheme of K3 surfaces. That was due to result of me with Francisco, and more recently, in much more generality, by result with me and Francisco, result of mine with my students, Devaditya, Ray Chaudhary, and Jayan Mukherjee. So these are in the boundary of the Hilbert scheme of K3 surfaces. So K3 surfaces degenerate to this. So, and so K3 carpet is like a fake K3 surface. It is a scheme, not nowhere reduced scheme, for which the dualizing sheaf is trivial and its H1 is 0, same invariance as K3. So we had characterized this in 1997, which has been used by other people like Eisenbert, Schreier, and all in recent times. Now, the point with K3 surface and K3 carpets is it's there's a conjecture on curves called Green's conjecture. So that is closely, intimately related to syzygies of K3 surfaces. And we want to give a different approach to these things using K3 carpets. So that is the point here. So here is a result. So if you take a smooth regular surface and let Y tilde be K3 carpet on Y, so Y is any smooth regular surface, and you take a carpet structure on Y, which is K3 carpet structure. You take a very ample line bundle. What we are saying is, if L satisfies MP plus 2 property on the reduced part, and reduced part, and NP property on the reduced part. So you take this line bundle L tilde on the non-reduced scheme and restrict it to the reduced part. If that satisfies property NP and then MP, then you have this Koszul cohomology group vanishing. So if you take a line bundle on a non-reduced scheme, if you take the restricted, if you take it to the reduced part, if it satisfies NP and MP, then you have this Koszul cohomology vanishing. This is interesting because you take Y to be, for example, in for example, P1 cross P1, simple thing. And you can have a K3 carpet structure on that. So those are anti-canonical rational surfaces. And we have a complete characterization of which line bundle satisfies NP property on those anti-canonical rational surfaces. And it's easier to deal with this MP property on a rational surface because it's arithmetically Cohen-Macaulay. So if you have NP and MP2 property on the rational surface, you can say something about K3 carpets. But once you have on K3 carpets, we can show sometimes some embeddings are arithmetically Cohen-Macaulay, So its Syzygy will be same as hyperplane section, which will be a ribbon. And we can show that that ribbon actually can be smoothed to a canonical curve. So this is another approach to Green's conjecture. So of course, Green's conjecture is proved in some generality, and this is another way of looking at it. There are other corollaries of this. So here is a corollary of this result. So if you take a smooth anti-canonical rational surface, L tilde is globally generated and ample line bundle on that non-reduced part on the thickening of Y, which is a K3 surface, K3 carpet, then you have this Koszul cohomology vanishing. So this, as we can see here, hyperplane section of an embedded K3 carpet is a canonical ribbon. If so, that canonical ribbon, that's a ribbon means what is a double structure. If the underlying if you look at the underlying part of the double structure, which is a rational curve, for example, then the Green's conjecture has been proved there by Diopurkar. But our situation is much more general. You can take a K3 carpet on any regular surface we are taking. Yeah, not all regular surface may actually allow that, but many do. So that means you get a ribbon structure on a non-rational curve. So you can have a higher genus curve and a ribbon structure on it. What happens to the canonical ribbon conjecture? That is Green's analog of Green's conjecture for ribbons. We don't know this. So this is one of the approaches here. And I stop my lecture. I hope I didn't shoot too much out.
No. So thank you very much, Purna.
Welcome.
We'll take a few questions. You can open your microphone and video and ask your question.
How can you see my face?
Well, we can see your face, of course.
Oh, you can. Okay.
Yeah.
So can I?
You can stop the sharing screen, then you can see everyone.
How do I stop sharing the screen? I'm very sorry for being so illiterate.
Go to the three dots once again.
Okay, fine. I got it. Yeah.
Yeah. Okay. All right. So any questions?
Okay, I will ask some
Yeah,
questions.
sure. Yeah, please.
So, Purna, most of the results you stated looks like you are. I'm asking questions from algebra point of view. Most of the questions most of the results you stated are results about finitely generated graded rings. Okay, so and then you are saying you are working over complex numbers. My first question is, how much of it this will work over algebraically closed field, even other fields, and where did you use the geometry? That's my number one question, and I'll wait for the second one later.
It's a good question. The geometry is used because the way we have to prove these Koszul cohomology groups. So we, as I said, we restrict it to some nice subvarieties in the of these varieties that we are interested in. So what subvarieties exist on these varieties is a good question. So that is where the geometry comes in. So once you do that, then it becomes pure homological algebra. It's about surjectivity of multiplication maps, and you have series of homological tricks. We reduce it to curves, and then we have multiplication maps, and you have all these vector bundle techniques coming into play. But
homological algebra is not a geometric thing. Not
correct.
necessarily. It is an algebraic thing again. Okay.
That is right.
All of the things that you stated can be, at least as a question, can be written as an algebra question and can be investigated.
Completely, it can be formalized into pure algebra. How do you prove those cohomology groups is what requires geometry. But everything is formal otherwise.
So I mean, so far what you guys have done, it requires geometry, but algebraists can try the same problem. Perhaps you have to reformulate. That's one question I'm.
But these are the homogeneous coordinate rings coming from a algebraic variety. So you have to use some property of the variety and its embedding to say something. I mean, how will you formally just prove formally? I mean, it's
How will you prove? That's the question you're asking, But
yeah. I mean, I don't
questions
know.
make sense. Questions make sense. Okay.
Yeah,
So
there are pure formal. You can. I understand what you are saying. For
yeah, you
example,
are
please
looking
tell
at
me.
Koszul complexes. Koszul complex is not a geometric thing. Okay.
No. I mean, yeah. No, what I'm saying is, it can be. I don't know how to reduce every one of the steps in my proof
No, you
to
cannot. Proof I'm not
algebra.
talking about. I'm not talking about proof. Proof is
Oh yeah,
somebody has to work on.
yeah.
Okay. Yeah, I mean, my follow-up question is that all the statements you made, if you simplify, you get a bunch of results. Okay. I'm asking, is it different? I mean, so if you simplify, you get those resolution in terms of twist of OX. Okay. So I mean, whether it changes anything. That's what I'm asking.
Here, but we are not sheafifying anything here.
You did not.
Yes.
That keeps it more algebraic
Yes.
than
Yeah,
geometric. Okay.
the things change if you do that, I think.
It
So,
does change. I mean, things. I mean, so that's the easier question. That will be an easier question if you simplify. Those are weaker results. Okay, and that may be useful. And I wonder why you geometrists, people like Lazarsfeld and all, are.
no, we do this, but I don't think you should ask somebody like Eisenberg who would know. I mean, for example,
Okay.
there are people here, experts, Watanabe, Professor Watanabe. I mean, they will be able to say it, I think.
Okay.
Yeah, I'm not.
Meaning these results can be useful for some of my purpose. This kind of resolution as yeah, I mean Koszul resolution of vector bundles and all that, and ideal shapes. Okay, yeah, thank you.
Welcome. Thanks for the question.
Are there any other questions? Yeah, Purna, I have a naive questions.
Please do.
I don't think I saw any result about smooth three-folds. When do they satisfy NP property?
No, oh yes. No. Even for surfaces, it's not known. First of all, if you take this, take curve. If you take canonical plus 3 times ample is very ample. If you take a surface, canonical plus at least 4 times a multiple of an ample is very ample. So you can ask these questions. That's what Mukai asked. For a threefold, you do not even know what a very ample line bundles are when it concerns adjunction. So if you take K plus, for example, 5A, is it very ample? Yeah, we don't know that. And even
Okay.
K plus, even some reasonable bound is not known. In fact, very recently, even so, for example, K, that's what called Fujita conjectures. So if you take K plus N plus 1 times an ample, is it base point free? K plus N plus 2 times an ample, is it very ample? So K plus, so it is completely open for 3 folds, 4 folds, and 5 folds. It is known for base point freeness, but ampleness, very ampleness is not known. And for example, my postdoc has proved actually a stunning result towards Fujita conjecture for base point freeness. I want to give publicity to that. It's open out in the open, attracted a lot of attention. He shows that if you take canonical plus of the order m times log n, n times log n times ample is actually base point free. And that is a very strong result for base point freeness. But very ample, we don't know. The result we do know is an Ein-Lazarsfeld result, where we take very ample line bundle and take K plus N plus 1 plus P, I think. at times ample is very NP. Of course, Francisco and I have optimal results for Calabi of three-folds. So that's kind of interesting things, very ampleness. So in general type, my students, Devaritya and Jayan, for their PhD thesis, showed the generalization of whatever I showed for any variety of higher dimension variety with the non-negative Kodaira dimension. They have proved that. Yeah. So for three folds, for example, they prove a very interesting result for three folds. So Kodaira Bangere showed that for a surface, 5 times kx is very ample, and Chiliberto and me showed it's projectively normal. My students show for threefold, 12 times kx is very ample, and embeds it as a projectively normal variety. Earlier, the other bounds are like 59, so they reduced it to 12.
Okay.
Yeah. Yeah.
Thank you. Thank you very much. Any other question?
Professor Watanabe, you have any comments to what?
Oh, sorry.
Did you have any thoughts on what Mandal was asking? And sorry to put you on spot, but I'm sure you will always have something interesting to say. So I wanted to know. That's fine.
Yeah. So in some sense, so in my opinion, prediction varieties are commutative rings.
Yes.
So many properties expressed in terms of ring theory.
Yes. Yes.
So, but
But as you can see, there's a lot of Japanese mathematics in my mathematics. I've been very heavily influenced by those kind of things. Type and Fujita,
yeah.
And
The algebraic geometry in Japan is very, very strong.
Of course, very much. Of course, remarkable. They're all my heroes, and it has a deep influence on what I'm doing. And it's a very strange thing here, a confluence of Japanese, Italian, and American. So I'm an Indian American, and there's vector bundle techniques, the Indian part perhaps of semi-stability and things like that. The ribbons and all are these objects introduced by Heisenberg actually, and Green. So this is kind of involved in there.
Yeah.
It's a confluence of various things, but there's a very decidedly very Japanese thing. In fact, in my other works on classification, which are and also generalization of Horikawa's results or n-folds, I always think, at heart I'm very Japanese Italian.
I am very glad that you evaluate Japanese mathematics so high.
Oh, of course. Who will not?
Okay.
It's deeply influenced. Thank you very much. Thank you, Jugal.
Yeah. So I requested Purna to play violin after his talk, but it may be too late for many people. And at some other point of time, we will have his concert also in this seminar. I'm just looking for a suitable date. He is a busy musician. Yeah.
By the way, Professor Watanabe is a fine pianist, and I have heard him play, and I think he has heard me play perhaps also.
Yeah.
You have heard me play.
We will have a Jugalbandi sometime.
So why not embed music in give background music for math talks?
Oh, please.
Yeah. So next week.
Hard time concentrating on one.
Okay. No, it will be nicer and smoother, to digest math.
Yeah.